In the last video, we proved the invertibility theorem for linear transformation, and we're going to use it to prove that a map is an isomorphism. All right, so here's the map. Show that T from R3 to R3, which sends x, y, z to x plus y plus z, is an isomorphism. All right, two things I need to prove. First, I need to prove it's linear, and then I need to prove it's an invertible map. But if you notice, once I know that I have a linear transformation, if I know that the two vector space have the same dimension, then I can, instead of proving this, I can just look at the kernel and show the kernel 0. That's what we'll do. All right, so first, T is a linear transformation. All right, so we'll do it in one step. I'm going to take T of V1 plus K V2. I'm putting arrows because these are vectors. So that would be T of X1, Y1, Z1 plus K X2, Y2, Z2. That's T of X1 plus K Y1, X2. Y1 plus K Y2, Z1 plus K Z2. And I'm going to apply the map. X stays X. Then I'm going to add X and Y for the second. And I'm going to add all three for the third. KY2. And let me move everything to the left. And Z1 plus KZ2. Oh, no. I was right before. All right, so I've applied T. This is what I got. All right, I want to prove that it's a split of T to V1 and K times T to V2. So let me start splitting things. I'm going to keep X1, Y1, Y1, Z1 on 1. So if I keep these, let's see what I have left. I have left kx2 in the first, I have kx2 plus ky2, and I have kx2 plus ky2 plus kz2 afterwards. And then I could factor k out right here. And I have T of V1 plus K T of V2. All right, so yes, T is a linear transformation. And second, I'm going to look at the kernel. I want to prove that the kernel is just 0. So let's take T of x, y, z. That's x, x plus y plus z. Let's assume that this is 0, 0, 0. I get that x is 0. I get that x plus y is 0. I get that x plus y plus z is 0. And so if I solve this, I mean, you could do it in your head. Once you know that x is 0, the second gives you y is 0. And once you know x and y are 0, you get z is 0. And so kernel of t, anything that's sent to 0 has to be 0. All right, let's look back at the theorem to show if we're done. Hopefully we're done because we don't have much room. Done by lack of space. All right, so I have a linear transformation, I need to check that the dimension of W was the same as the dimension of V, and then this is enough, it's equivalent. All right, so I just need that little thing. All right, so dimension of V equals dimension of R3, so that's 3, and dimension of W is the dimension of R3. That's what we had. It's 3 as well. And so we can apply the theorem by the invertibility theorem. By the invertibility theorem, kernel of T is 0 means T is an isomorphism. All right, so if your domain and codomain have the same dimension, all you have to prove is that it's linear and that the kernel is 0, or linear and the image is W, whichever one you rather. All right, in the following sections, we'll be looking at linear transformation in Rn. So something we're more comfortable with, something we know well, and something we're very interested in. We'll see how all of these results apply in that setting.